Hi guys, this is Jonathan Lambert with the Mathematics Development and Support Service at the National College of Ireland. And this short video is going to attempt to demystify the logic that's associated with an ANOVA, or more importantly an analysis of variance hypothesis test. I suppose let's just keep in mind that an ANOVA is undertaken. So ANOVA, we undertake an ANOVA, when we have more than two levels of measurement, when we have more than two levels of measurement on the independent variable, two levels of measurement, okay, on our independent variable, okay, okay. So for example, we might conduct an experiment where we try to ascertain the spending price or the spending behavior of students. We might break the students up into three groups. Let's say our students are broken up into three groups where we have 20 to 30 years old students, we have 30 to 40-year-old students, and we have 40 to 50-year-old students. Okay, so we have three groups. These represent, so here's our groups. Okay, the groups are classified based on the age of the respondent. Okay, and maybe we've asked a particular question to all respondents, and the question was, how much did you spend over the weekend, or how much did you spend last week? And maybe the 20 to 30-year-olds spent, let's say, 50, 60, 70, 65, and let's say 80 euros. Let's say the 30 to 40-year-olds, let's say they spent, let's say for argument's sake, they spent 70, 75, 62, 92, 104. And let's say the 40 to 50-year-olds, let's say that they spent 150, 250, 175, let's say 110. Let's just say that we actually only asked for 40 to 50-year-olds this particular question. Okay, so we have three groups. Okay. Now you might ask the question, well, if I want to find out whether there's differences across groups, or differences, between groups, why don't I just run a number of independent samples t-tests? Okay, and there's a reason why we don't run a number of independent samples t-tests, and it's got to do with the significance level associated with each test. Let's say that the tests are being conducted, let's say our independent samples t-tests, t-tests are being conducted, let's say, with an alpha value of 0.05. Okay, this is the probability of committing a type 1 error. So this is our probability of committing a type 1 error. Okay, so the number of ways that we could run independent samples tests is, let's say this is group A, group B and group C, is we could compare group A against group B to see whether there's a significant difference between the average spend of group A compared to group B. We could compare group A against group C, or we could compare group B against group C, each one having an alpha value associated with the actual test itself. Okay. Now, the question that we're trying to answer when it comes to an ANOVA is whether at least one of the possible pairings of groups are significantly different. At least one. It could be that A is different to B. It could be A is different to C. It could be B is different to C. It could be A is different to B and A is different to C. It could be A is different to B and B is different to C. Or it could be all three are different. Okay, and an ANOVA allows to control for the experiment-wise type 1 error rate by setting a specific value for the test. Okay, so let's just assume that we undertake individual t-tests. So let's assume we run t-tests. Okay, now the probability of us committing a type 1 error, that's us rejecting the null hypothesis when we shouldn't have rejected the null hypothesis, okay, is 0.05. Okay, so the probability of us not rejecting the null or failing to reject the null. Okay, so the probability of us not committing, okay, a type 1 error, is I suppose it's 1 minus 0.05. Yeah, okay, so it's 1 minus 0.05. Okay, so let's assume in this particular case that we have 3 tests. Okay, so the probability of us not committing a type 1 error across the 3 tests, okay, would be the probability that in test, let's say test 1, test 2, test 3, okay, would be the probability that test 1 has no type 1 error, okay, and test 2 has no type 1 error, okay, and test 3 has no type 1 error, okay, or that we don't commit a type 1 error. Okay, that's the total probability of us not committing any type 1 errors when we run 3 separate independent samples t-tests. Now, the rules of probability would suggest to us, in the case of where we have independence across experiments, okay, which is one of the conditions associated with ANOVA and one of the conditions associated with the independent samples t-test, is that the probability of an AND is simply equal to the product of the individual probabilities. Okay, so the probability of this whole condition here, which represents not committing any type 1 error, okay, is simply the product of the individual probabilities. Now, the probability that we don't commit a type 1 error when we conduct the experiment A versus B is 1 minus 0.05. So it's 1 minus 0.05 times the probability that we don't commit a type 1 error when we run experiment 2 is 1 minus 0.05 times the probability that we don't commit a type 1 error when we run experiment B against C, which is 1 minus 0.05. Or it's equal to 0.95 raised to the power of 3. Okay? Now 0.95 raised to the power of 3 is 0.95 raised to the power of 3, which gives us a value of 0.86, or 0. When we round to 2 decimal places, gives us a probability of 0.86. So when we run 3 separate independent samples t-tests, the probability of us not committing any type error across these particular tests, yeah, okay, if we just run 3 of them, yeah, okay, is 0.86. Okay, that's the probability of us not committing a type 1 error, which means that the probability of us committing a type 1 error, the probability of an error, okay, must be equal to 1 minus 0.86, which is equal to 0.14 or 14%. Okay. So what we can actually see, hopefully here, is that the reason why we don't do pairwise independent samples t-tests is because the probability of committing a type 1 error, although it's set at 0.05 for each test, across the whole experiment where we're interested in finding a difference across any of the groups, the type 1 error rate explodes in this case to 14%. Okay, so that's an important point in relation to the logic behind an ANOVA, or why we do an ANOVA and we don't do independent samples tests. Yeah. So what is an ANOVA all about, and what is an ANOVA? How does an ANOVA find a difference across either of these particular groups? Okay. So what we need to do is this, is that I suppose we need to consider the distributions associated with each of our groups, first of all. Okay? So each one of our groups, Group A, Group B and Group C, has a particular distribution. So Group A, okay, which is the 20 to 30 years of age guys, okay, has a distribution. So it has a particular distribution that has a particular mean value. Let's assume it's the population mean, okay, for that particular group where it's been selected from. So it's mu of A. Group B also has a distribution. Okay, Group B. This is for the 30 to 40 years of age. Okay, that also has a distribution. It might be a little bit different. Okay, it might be in around here. A different standard deviation to the previous one. And Group C also, which is the 40 to 50 years of age, also have a distribution that has a center point, so it has a center point or a mean value. Okay? So each one of our groups has a particular distribution associated with it. Now the logic behind the test is this, is how we figure out that there's a difference across at least one of the groups, is we consider each distribution on the same continuum. Okay, so we consider each distribution on the same continuum. Let's say we have distribution A, so this is for group A. We have distribution, let's say B, this is for group B, and we have distribution, let's say we have distribution C, which is, let's say, down here, so this is for group C. Okay, so how the hell are we going to figure out whether there's a difference across the groups? Okay, well, I suppose the first thing that we do is that we need a way of measuring the average distance between groups and also the average distance within groups. And these two measures are going to allow us to construct a ratio where this ratio, if it's large, is going to be evidence to suggest that there is a difference, and if it's small, it's going to be evidence to suggest that there's no difference. So what we first of all do is we construct what's known as the global mean. Okay, so we construct the global mean. What that basically means is we take all of our observations, all of the observations in group A, in group B, and group C, and we pool them all together. Okay, so we have a large data set now that has all the observations in A, B, and C. We pool them all together and we calculate a global mean value. Okay, so let's say this is our global mean. Okay, let's call this, let's say this is x bar of g, or this is our global mean value. Okay. Now what we do is this, is we check to see how far each of our distributions, and we know where our distributions are centered because we have the averages for those particular distributions. We check how far each of our distributions is away from this particular global mean value. Okay. Now we have a formula that allows us to do that. Okay. This is our between measure. Okay, so what we have is we have a between measure formula that says that the sum of squares between is simply equal to the distance that each mean value or each group mean value is away from the global mean. Okay, x bar of g, and we square that, and we do that for them all. Okay, so we calculate this for all of the groups. Okay, that we have, and what this gives us is, I suppose, it gives us the total square distance that our group means are away from this global mean. So this is a measure of dispersion. Yeah. Okay. Now there's a little modification that we make here. We actually calculate the average of this, so we calculate the mean sum of squares between. Okay, by dividing this by how many groups we have minus 1. And we also, I suppose, we take into consideration the individual group sizes, okay, when we make this calculation. But effectively, this mean sum of squares between measure, this mean sum of squares between measure, okay, effectively this mean sum of squares between measure is telling us on average, yeah, because we're dividing by how many groups we have, although we're subtracting 1, it tells us on average what the square distance is that the groups are away from this global mean value. Okay, so that's our first measure to keep in mind. Okay, our second measure that we have, okay, is a measure where we calculate how skinny, okay, or how wide on average the actual individual distributions are. Okay, so our second measure, okay, let's take this distribution again over here. Okay, so we have group B. Let's say we have group A and we have group C. Okay, so the second measure, what we do is we calculate, I suppose, within each group, okay, how skinny the groups are themselves. Okay, so we calculate a measure of, well, I suppose we're really calculating a measure of variance, yeah, that tells us how skinny each of our individual groups are. The test statistic for that is, well, what we need to do is for each observation, okay, we take away the mean value of the group itself and we square it, and we sum these up for all of our observations. Okay, so for each group that we have, we calculate how far individual observations are away from their own respective group mean. Okay, and we divide this by how many observations we have in total, n, minus how many group sizes, how many groups we have. Okay? just keep in mind here is that as n gets large, the number of groups won't really influence this particular number. But effectively, what we're calculating is we're calculating an average. It's the average square distance that individual observations are away from their own group. Okay, so this particular measure here is known as the mean sum of squares. The mean sum of squares between. Sorry, the mean sum of squares within measure, okay, because we're measuring them within the groups themselves. Okay, so this is the mean sum of squares within. Okay, so now we have two measures of variance. Okay, we have the mean sum of squares between, that tells us how far on average our distributions are away from each other or away from a global center point. Okay, and we have the mean sum of squares within, which tells us how, on average, how skinny or how broad our distributions are. Okay, now equipped with both of these measures, okay, we construct what's known as a test statistic. Okay, so equipped with let's say the mean sum of squares between measure and the mean sum of squares within measure. Okay, let's just keep in mind that the mean sum of squares within measure is how skinny each distribution is. Okay, how skinny each distribution is. Okay, and the mean sum of squares between is on average. Okay, how far are the distributions or the groups? Okay, are the distributions away from each other. Okay. So what we do is we calculate the ratio of the between measure to the within measure. So we construct what's known as an F-statistic. Don't forget our F-statistic is set up to actually calculate the difference between two variances. Okay. So our F-statistic is equal to it's the ratio of two variances. Now don't forget, effectively what we calculated when we did the between measure was a sum of squared deviations. Yeah, okay, so actually this is a measure of variance. Okay, so what we have is our mean sum of squares between measure goes in here, and also let's keep in mind that our mean sum of squares within measure, okay, is also a measure of variance. It's how far on average observations are away from their own mean value, okay, or their own center value. So we have a mean sum of squares within measure. Okay, so the question is, how do we interpret this particular test statistic? Okay, and I suppose there's a number of ways of trying to interpret this if we consider whether these values are large or small, okay, relative to each other. Okay, relative to each other. Okay, and let's just do a scenario. Okay, let's say for argument's sake that the between measure is large, and let's say the within measure, is small. So if I was to draw a graph of that, what that basically means is that on average the groups are far apart from each other. Okay, so on average the groups are far apart from each other. Okay, and on average the groups are small, or the groups are skinny. Okay, so what we have is we might have something like this, and we might have something like this, and we might have something like this. They're far apart on average, okay, which means that at least one of them must be a good distance away from the others, and on average they're small within, okay, which is our evidence to suggest that at least one of our groups, in this case this group here, is different to the other two, or is different to at least one of the others. Okay, that's one way we could interpret this. Yeah. The other way that we could interpret it is that the between measure is small, okay, and the within measure, okay, is small, okay. So it's also possible that our groups are relatively close to each other on average, groups A, B, and C, okay. But their within measure, how skinny they are, is really, really small relative to the smallness of how far they are apart. So we have a distribution that looks like this. So maybe it's very skinny, and maybe this one is very skinny, and maybe this one on average is also skinny. So once again, we don't have much shared area. Evidence to suggest that there's some difference. Okay. The other possibilities are that we have large, large, and that we have small, large. Okay, so let's say our between is, let's say, is small, and relative to that, our within measure is large. Okay, so what we know now is this, is that our distributions are close together. On average, they're close, and the within measure, so they're close together, their between measure is small, and their within measure is large, which means that the distributions are pretty big, if that makes sense. Okay, so the distributions have an average variance within that is quite large. Okay, which is evidence to suggest that they share lots of area. Okay, which is evidence to suggest that there's no difference between them. Okay, so this F-statistic is a really, really important statistic when it comes to the interpretation of our ANOVA value. If the F value is large, okay, so if the F value is large, it's an F distribution. Okay, an F distribution, okay, is modeling this. Okay, if the F statistic is large, we'll be out in a tail. Okay, if it's large. Okay, if it's small, we won't be in a tail. Okay, so the F value is small. And once again, we've already set a rejection region. If the F value is large enough and falls into the rejection region, well, then we know that we reject the null hypothesis. So what is the hypothesis associated with an ANOVA? Okay, so the hypothesis, depending on how many groups we have, the hypothesis that's associated with ANOVA, well, once again, we have a null position and we have an alternative position. The null position is that there's no difference between our groups. In other words, that the average of the first group is the same as the average of the second group, which is the same as the average of the third group, which is the same as the average of the fourth group, the fifth group, and it's the same as the average of the nth group, okay, depending on how many groups we have. And the alternative is that at least one of these particular positions, okay, or at least one of these particular mean values is different to some other mean. Now we just write it in this fashion here. Okay, this does mathematically say that they're all different to each other. Okay, but our interpretation, just from a shorthand perspective, our interpretation of this particular line here is that at least, okay, one group, okay, has a mean different to another group. Okay, and that's our default position. That's our hypothesis. Once again, our significance of our test is alpha is equal to 0.05 typically. Our test statistic, okay, is f is equal to the mean sum of squares between divided by the mean sum of squares within. In a later video, I will detail how to calculate these particular mean sums of squares between and the mean sums of squares within when we have some data to work off. Okay, and our critical values, okay, our critical values are based off an F distribution. Okay, it's important to note that an ANOVA is a one-tailed test. Okay, it's a one-tailed test, so we put all of our alpha in the tail here, and the question is, what is this critical value that has, in our case, 0.05 of the area to the right hand side? Okay, well, it's based off degrees of freedom. Okay, so our degrees of freedom of the between measure go here from our F distribution table perspective. The degrees of freedom of our within measure are listed down here. Okay, and we triangulate in, and this gives us our critical value. Okay, our decision is going to be, well, if F is bigger than C, we reject. Okay, otherwise we fail. Otherwise we fail to reject. Okay, fail to reject. Okay guys, I know that was quite long. That was probably about 25 minutes there, but I hope that this short video, or this video, helped to demystify the logic associated with an ANOVA. Okay. Once again, this was Jonathan Lambert with the Mathematics Development and Support Service at the National College of Ireland. Thanks for your time. Okay, bye bye.